Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Fanta In Space, released in 2008, code by Sound Demon and The Human Code Machine, and music by Fanta. This demo is unusual because it's the first demo that had 4 sample channels with filter with 8-bit samples and 2 SID channels. We're going to have a look at the routines on how it creates these samples, but let's listen to some of the music in the background first. We can see from this that there's quite a lot of memory reading going on in the memory debug view there. Let's go back to the I/O view where we can see the SID chip state. So I can click off each of the voices. So let's click off that one, and we don't have any digis. We just have the 2 SID channels. If I just have one SID channel, we can hear what that's doing, and then the other SID channel is doing this very quiet instrument. But then the third SID channel, which is mostly playing a triangle waveform in inverted commas, that creates all of the digital sound effects. So normally samples on the Commodore 64 are played by altering the SID volume register, which is a 4-bit value, so values from 0 to 15, which alters the volume for all 3 SID channels. But if you change the volume channel, you can actually get 4-bit samples playing out of it, because it basically causes a click at different volumes, which then comes through as a waveform. However, this demo is using channel 3, which is rapidly alternating between triangle and not triangle waveforms. So now I've got the code stopped. We can see that we've got code which executes rapid updates, not to the filter channel, or not to the volume channel, which is a D418, but we've got code here. Because it's paused, I can move the targeting cursor around. We can see that we've got code altering D412, D40F. D412 and D40F is the third SID voice waveform control, plus also the third SID voice frequency control. So D412 is the waveform control, and it's alternating from 1-1, which is triangle plus gate, and then it's going to 0-9, and 0-9 are bits 8 and 1 added together. So 8 and 1 are basically moving the voice control into what is called the test mode. It's then loading a value from F320 and storing it into D40F. But yeah, basically bit 3 is test, and bit 1, or bit 0 rather, is voice on, if it's set, which is the gate for the voice. So F320 looks like it's reading from a buffer and then storing into D40F. So D40F is the frequency control for the third voice on the SID chip. There we go. It's frequency high, actually, not frequency low. The frequency on each of the SID voices is actually 2 bytes long, so 16 bits. And then this routine, once it sets up the frequency for the voice, it's then incrementing 4B, and 4B is the low byte of that absolute load there from the buffer at F320, F300 to F3FF. Basically, it's self-modifying code. So this inc there is just altering the low byte of that absolute load there. And then it's loading the accumulator back, because the accumulator was stored as part of the interrupt entry routine, and it's jumping back to DD0C. So this store A there, store A 58, and 58 is self-modifying that load immediate there so that it will restore the accumulator, and then DD0C contains RTI. So DD0C is actually in the CIA2 control registers as well. So DD0C contains RTI, but DD0D is actually CIA2 interrupt control. And when you read from that, it acknowledges the interrupt that occurred, and then it allows the interrupt to happen again. So basically, by jumping to DD0C, which contains RTI, the 6502 will actually read RTI back. Will read the byte after the RTI instruction as well, which self-acknowledges the interrupt caused by CIA2, which is the non-maskable interrupt vector, right? So we have the non-maskable interrupt vector, which we just saw at the end of memory, pointing to a routine which contains, in memory, it contains 4C0034. So DC04, which is the 4C instruction, 4C is jump. Right? And then we've got a low byte, which is 0, but the high byte, or rather the low byte of timer B, which is the high byte of the jump address, is constantly changing. And we've got a timer there set up so that it seems to be rotating around values from around about 0 to probably about 3F, which is correspondingly, it's not a coincidence, but it basically looks like it's the number of cycles, maximum number of cycles in a scan line. So we have a hardware timer self-modified jump leading into jumps from the non-mask to the non-maskable interrupt, which are self-modified by the low byte of the timer, which corresponds to the high byte of the jump. So what this does is that it causes the non-maskable interrupt to start executing different code in different memory pages, aligned to 256 bytes each, or 100 bytes in hex. And the non-maskable interrupt will start executing different code depending on the precise value of the timer. So if we trace this execution here, we can see that sometimes that code will execute code at 200, sometimes it will execute code at 300, 400 in hex, 500, and so on and so forth. Now, because the non-maskable interrupt is timed to occur at a specific number of it wants to occur at a precise point in the VIC chip, in the CPU and VIC line execution. But because there are instructions before this executing in the main line which are of variable lengths, it uses this self-modified hardware self-modified timer value feeding into the non-maskable interrupt jump to execute different code before it really starts needing to execute the interrupt there at the real main interrupt code for playing the sample at 40 in hex. So although 40, the hex address 40 rather, starts executing that load accumulator instruction at the same cycle on the scan line, the previous code has different lengths of instructions, different lengths of all of the opcodes leading up to that point. And that's the self-modified code. So the code at 800 does a store to 0 page and then 3 no-ops, which wastes a certain number of cycles or aligns a certain number of cycles before it gets to the jump 40, and then that jumps to code. So basically we have the timer value hardware self-modifying the jump instruction which jumps to different code, which then runs different code of different lengths in terms of CPU cycles to precisely align the start of the sample play code routine, which I think is incredibly clever. I don't see this very often. It does use quite a lot of code, and it uses quite a lot of code over potentially a large range of memory. But because the non-maskable interrupt is kind of like timed to appear or to want to start executing at a specific narrow range of cycles going down the screen there, and you can see that there now as I've inserted the inc D020 instruction which increments the border color. You can see that the border color starts changing at precisely the same cycle all the way down the left-hand edge of the screen. So that somewhat narrows the variable range of that self-modified jump, I have a feeling, into these different little fragments of code which self-correct the timing of this update. Now, why go through all of this trouble to try and use the timers in this way to execute different precisely timed code to compensate? Now, the reason is because when you're playing samples, whether or not it's proper filtered digi samples by using a triangle waveform, or if you're using D418, which is the volume register update, if you have variation or very small cycle variation in triggering a new sample volume, then you will get very small variations in the frequency, the amplitude, but also the frequency of the samples that you're trying to do. And you get kind of like a carrier signal, or you get like a harmonic, if you like, or an unwanted frequency, depending on the amount of wobble you have when you're updating the volume register. Then you get a harmonic or an unwanted frequency playing through the SID. So the three no-ops that I replaced with inc D020, the three no-ops add up to 6 cycles, and inc D020 is 6 cycles. That's why it didn't affect the quality of the sample playback by adding the border register update there. So yeah, this is a really, really, really clever way of precisely timing a non-maskable interrupt, or compensating for the cycle variability in previous instructions in the mainline previous to when the interrupt starts. Okay, so the code outside the mainline is not idle. The code outside the mainline seems to be busily calculating stuff in the background. So just to recap the interrupt stuff, first of all, we've got the CIA1 self-modifying code, self-modifying a jump, which compensates the CIA execution of the non-maskable interrupt at precisely the right cycle, or this very specific cycle, on a specific raster line, every other raster line basically. And then it's basically reading all of these pre-calculated samples from that memory range, F300 to F3FF. And then when the interrupt finishes updating the sample, it then loops back to that RTI instruction, also in CIA2, which then acknowledges the CIA2 interrupt control. So yeah, really, really clever way of doing it. Let's see if we can look now at the code which is adding information into the sample buffer F300 to F3FF. So yeah, the triangle test bit frequency interaction is important here. Because the triangle waveform is rapidly switched with the test bit at different frequencies, it causes effectively the SID chip to want to start playing a sample at a particular volume because it's seeking with different frequencies up or down the triangle waveform. And the rapid toggling of the test bit is to get the SID chip to reset its internal waveform generation, so that the amount of frequency used relates directly to volume for the output SID voice, for the third voice, which is using the triangle waveform. But it's not using a triangle waveform, it's just using the frequency of the triangle waveform to seek up or down the gradient of the waveform, triangle waveform, to seek for a particular volume and then sustain that volume until it needs to change that volume again. And because the SID voice itself, the waveform from the SID voice itself, which is calculated into seeking to a particular volume to play samples, because it comes from the SID voice, then the output from the SID voice then can get passed through the final SID filtering control from the volume register, which also contains the filter control and everything like that. And that's why the digital samples are being affected by the final output filter control with the SID. Normal volume controlled samples from the D418 register, the volume register, are not usually affected by the output filters, because the output filters only act upon the cumulative waveform output from the earlier stage in the SID chip. So here we are in ICU 64, and let's put a breakpoint at 4A and continue on the execution. There we go. There's the load from 4.3 whatever into D40F, which is the high frequency for the third SID waveform, or third SID voice, rather, sorry. Let's put a break on DC04, and we can see there that it's the jump. And then in this case, the jump goes to 800 in hex. We'll modify the code so it does the inc D020 instruction again, so that at least we've got some colorful bars on the screen rather than the black screen. All of this code here, which stores into F380, is rather fast code, but basically what it's doing is that it's accumulating 1, 2, 3, looks like 4 different values into the sample buffer at F380. 1, 2, 3, 4, yes. So it's accumulating together 4 different, effectively 4 up to 4 different mixed sample values into the output sample buffer at F300 to F3FF, and it's doing an increment Y. So Y starts at 0 in this routine, and it goes up until Y is while Y is plus, so any value from 0 to 7F. It loops around this loop, filling in basically 128 values. And because a memory page is 256 values, it's filling half a memory page. And it's either filling F300, or if I move ahead with the next iteration through this loop, it's going to be filling in F380, right? So let's run ahead with the execution and see where it self-modifies this code. So the next iteration of this code, there we go, it's storing into F380 now rather than F300. So yes, it's filling alternate halves of the same memory page at F300 to F3FF. And it's doing that opposite to what the sample play non-maskable interrupt is doing. So while the non-maskable interrupt is playing sample memory or samples from memory range F380 to F3FF, this routine in the mainline is calculating samples into the memory range F300 to F37F. And then when the sample play starts playing samples from the beginning of the memory page, it's calculating samples into the end of the memory page. So we have 2 independent buffers here which get swapped over. While one is playing samples, the other one is getting samples calculated into it, and then vice versa. Let's see if I can get that easily visualized in the memory view. Actually, at the beginning of the memory, I've just noticed this little range of memory here. So when we have samples which are quite loud going on, it seems to be reading from plus or minus the middle range of this memory table here. That might be like a volume lookup for the final mixed sample, perhaps, because there probably needs to be something which takes mixed sample values and then converts it into like a final volume or a frequency range to then convert it to volume, I expect, perhaps. Anyway, so let's use the step command to step 20 instructions, and then if I zoom in down to the bottom of the memory here, and as I execute blocks of 20 instructions, there we go, there's the memory page at F300. So let's keep an eye on this. Now remember, memory reading is green and memory writes are shown in yellow. So let's step over 64 instructions at a time. And we should be able to see it now quite clearly. So the bottom two lines, the yellow bar on the right is writing samples to F380 to F3FF, and then the bar on the left, the green bar on the left, is reading samples. Now when the green bar on the left then moves to the right hand edge or right hand side, so the second sample buffer, it's reading samples from the second buffer, it's writing samples to the first half of the buffer, so the first buffer on the left hand side there. So there's the yellow writes there on the left, and then the green reads are on the right, and then the green reads on the right will eventually loop back to on the left again, and once samples are being read from the left, samples are being calculated, written into the second buffer on the right there with the yellow writes. And if we look, we can see that the sample buffer writes complete just before it's going to get the sample read, green reads, start in that same area of memory. So the sample calculating and mixing routine is just a little bit quicker than the time taken to read samples from the other bit of memory. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.